Welcome back to my channel. In our last video we started with the maximum independent set, and in this video we're going to solve an example using everything we learned from the last video. But before we dive into this example as it is on my screen, let's talk about real applications of maximum independent set for a minute. So the maximum independent set is very useful in fields like in bioinformatics, which I would not like to delve in, but let's talk about its applications in scheduling. If you can remember the famous phone station problem, I think I talked about it in the beginning of this playlist when we were treating greedy algorithms. We talked about how to maximize our phone stations if one phone station would serve people 4 miles away from it. So if you remember correctly, we said that if this is the beginning of that town, right, and this is 4 miles, we could put the first phone station here, and in this next 4 miles, this phone station will cover this and this, right? So in a way, you can look at this as maximum independent set, because if this first phone station covers this 4 miles and this 4 miles, and we have another 4 miles here, and we have another phone station here, these two phone stations, 1 and 2, are not connected. Supposing each connection is per 4 miles, they are not connected. So we could look at it as maximum independent set. So all I'm trying to say is that maximum independent set is used for job scheduling and network design. So it's valuable for task scheduling, is valuable for network design to ensure that all of your tasks are performed efficiently without conflict. And it's also used for maximizing resources when you are covering a location, using a click partition. So you can apply maximum independent set in your network design, just like in the example I gave. It helps to optimize placement of resources in a facility over a given area. So let's take a look at the example on the screen. You can pause this video for 1 minute, read through the example, and you get right back. So basically, we want to solve this example, and the central idea is that in maximum independent sets, the maximum independent set in G is corresponding to a maximum independent set of non-overlapping intervals. So what that means is that we are going to organize or arrange our intervals according to their finish time. So if we sort our intervals according to their finish time, our maximum independent set will be intervals that do not overlap. So let's try to use a diagram to express this. Let's say let's call this interval 1, I1. Let's call this another interval. Let's call this interval 2. Let's call this interval 3. Let's call this interval 4. And so on and so forth. Let's call this interval 5. We see that interval 1 overlaps with, let's say it overlaps with this and overlaps with this. Interval 1 overlaps with interval 2 and interval 3. But interval 1 does not overlap with interval 4 and 5. Instead, interval 3, 4, 5 overlaps. Let's say this and this, they overlap. So we are going to be looking at all intervals from intervals 1 to n just in the same way. We want to find intervals that overlap and intervals that do not overlap. So everything I've said so far is that interval 1 overlaps with intervals 2 and intervals 3, while interval 1 does not overlap, or you can say is independent of interval 4 and interval 5. So what does this mean? This means that let's write a recursive substructure with this information. So this means that our maximum independent set would be 0 if the intervals overlap. So if all intervals overlap, maximum independent set will be 0. I hope that makes sense intuitively, because like I said, intervals 1, 2, 3 overlap. That means they are dependent. Supposing we were to run 3 tasks that have these 3 intervals, I mean time intervals of 1, 2, 3, it means that we would have to pick one of them. So it means they are dependent. The possibility of carrying out the task that has interval 2 is dependent on 1 and 3. So it means they're dependent. Let's use that word, they overlap. So it's not it's not independent. So our maximum independence set, if all intervals overlap, will be 0. So that's the first case. So for overlapping, in let's say overlapping, but when there are no overlapping, we would have the same notation we had in the last video. We would have that here. We have a maximum 1 plus, let's call this a, comma, a minus 1. Now let me explain what this means. So let's a be the set which includes interval 1 but does not include its overlapping intervals. So let me repeat that. A set A includes interval 1 but does not include its overlapping intervals. That means that set A minus 1 would be another set that does not include A. And a maximum set A minus 1 that does not include A would include all the other sets that are not in A, which also do not overlap. I hope that makes sense. For example, let's draw a diagram from the last lesson. Supposing we have 1, then we have 2, 3, we have 4, 5, 6, 7. So let's say maximum independent set A. That means, let's say this is A, right? So it is this inclusive, A inclusive, and because 2 and 3 overlaps or is connected to A or are connected to A, this would not be in the set A. So we'd have this. So maximum independent set A minus 1 would be a set that does not include A. I hope that makes sense. So that would be this, and this is included in A. So whatever the children of this would be. So the maximum independent set of A minus 1 would be this, because it does not include A, and all other elements that are not in A. So this would be our recursive structure. So this is our recursive structure. So for our optimal substructure, we just want to select I. If we select I, then we skip all overlapping intervals. So if we, for our optimal substructure, if we select any interval, we skip every other interval that overlaps with it. And if interval I is not selected, right, then we include all overlapping intervals of I. So that's optimal substructure. I think I should say that again. So If we select, let's say, an interval I, then we will skip all overlapping intervals of I. But if we do not select interval I, then we are going to include all intervals that overlap with I. It's sort of like saying everything that I said in recursive substructure, but just in another way. So to write that down, let's say OPTI means optimal substructure of I. So what that is, so we have, but in this case we have maximum 1 plus OPTI, comma OPT. This is just a way of writing everything I've said right now. You have OPT I minus 1. We've solved the first part, converting our recursive structure to an optimal substructure that would help tabular computation. So yeah, we've answered the question. I hope the answer made sense. If you did like this video, please remember to subscribe. So next, let's write a dynamic programming based algorithm for this problem. That's the last part. So to write that, this dynamic algorithm would use a 1D table T. Let's call that 1D table T. It would use a 1D table T to store values for each I for 0 less than or equals I less than or equals n. So the optimal substructure, just as we had written before, is as follows. Let's call it T now, because we're working with a table called T, and 0 when everything overlaps, just as we said. But in this case, because this is a table, we interpret this 0 to be if I is equal 0. That's when there is no interval, right? So our table is going to start from 0 if I is equal 0 when there is no interval. But the formula for the substructure, as we had defined before, now we are going to be using T because we are now working with the table. So the formula for the substructure would be T, let's call this Pi plus 1 plus 1 plus 1 if I is greater than or equals 1. So the algorithm is as follows. So we have our inputs. Our inputs would be, this is our input, sorted intervals, going from intervals 1, intervals 2, to intervals n. So our first index, that's T0, right? The first item in our table would be 0 because there's no interval yet. So for I equals 1 to n, what's going to happen? We are going to apply this recursive structure. We have max, just like I explained before, T minus 1. This is T minus 1. So we're going to choose the maximum between these two. And the interpretation of this is same as I had explained before, where this is I inclusive and this does not include I. That means this set here includes whatever I is and every other interval that does not overlap with it. And this would be exactly the opposite of this, because it would not include I and it would include every other interval that overlaps with I. So it would not include I. So I minus 1 does not include I, right? So does not include I, negation I, if that makes sense, and every other thing that overlaps with I. So this answers the question. I hope you enjoyed this video. If you did, please remember to subscribe and like and comment, share. I'll see you on the next one.